It's good to have you back. Now, let's try to solve for the remainder if we are going to divide this f of x being 6x cubed minus x squared plus 2x plus 2 with a binomial divisor g of x being equal to 3x plus 1. If it's the remainder that we are only concerned about, we don't necessarily need to use here syntactic division or the long division just for us to solve for the remainder. We have what we call as the remainder theorem to be used in this concern. The remainder theorem allows us to decide a certain constant taken from our divisor, which can be substituted on our dividend, and whatever will be the result after substituting such constant, that is automatically the remainder. Let me rewrite here our given function. You have f of x, and we need the entire given. You have 6x cubed minus x squared. You have plus 2x here and plus 2. So this entire dividend will be divided by this divisor, g of x. Our g of x is 3x plus 1. Now, we are going to substitute here a certain constant that once we are done substituting whatever will be the result, that is automatically the remainder when this function is to be divided by this. The certain c will be taken from our divisor. Here, it's not 1 nor negative 1 because the structure should be x, not 3x. This means, let's try to divide this g of x. Just divide this by 3. So once you will divide that, your first term will become x only as 3 over 3, and your second term is positive 1/3. But the c is not yet 1/3 because the structure should be minus c. We can also rewrite this as minus negative 1/3. This follows the reverse operation of our double negative property, because if we have a double negative here, it automatically means addition. In this manner, since x minus c, and we have now x minus negative 1/3, our c is automatically negative 1/3. This is the value that we are going to substitute here, negative 1/3. And by substituting, meaning we are to substitute this to all the x variables in our dividend. So we have here negative 1/3, but you need to cube that, minus negative 1/3, and you square that, plus 2 times negative 1/3, and finally you have your constant plus 2. Simply simplify this set of operations, and the result would be automatically, according to the remainder theorem, is the remainder when this function is divided by this. So let's do it step by step. You have 6 times the cube of a negative number is still a negative. So the cube of 1 is 1. The cube of 3 is 27. Next, do not use the double negative property here. You still have minus. It's because we have the exponentiation here. The square of a negative number is positive. The square of 1 is 1. The square of 3 is 9. Here, since this is 2 over 1, you will simply multiply numerator, numerator, denominator, denominator. Positive 2 times negative 1 is negative 2 over 3. And finally, plus 2. Now, here, we can simplify this further. Since 6 and 27 has a factor of 3, we have here 2 and we have here 9. Because 6 is 3 times 2, 27 is 3 times 9, and cancel that out. So we have 2 times negative 1, that's negative 2 over 9. To be followed with minus 1 over 9. Here, minus 2/3 and plus 2. Now, we have a set of fractions here, including a integer, but you just need to look for LCD to combine them into one. Without using any calculators, the LCD is 9. 9 divided by 9 is 1, so we have negative 2 here as still. 9 divided by 9 is still 1, so we have minus 1 here. 9 divided by 3 is to 3 times 2, we have 6, so we have here minus. And then 9, of course, we know this to have over 1 rather. 9 divided by 1 is 9, times 2, we have positive 18. Look at the result of our numerator. Negative 2 minus 1 is negative 3, minus 6 is a negative 9. Plus 18 is positive 9 over 9, which gives us a final result of 1. This 1, according to the remainder theorem, is the remainder when f of x is to be divided by this g of x using c, which is negative 1/3. You can verify this result using synthetic division. But in this case, according to the Remainder Theorem, this is already the correct answer. That's all for today. You're dismissed. And please do not forget to subscribe now.